Well, welcome back, everyone. Hope you had a good spring break. So today what I want to talk about is I want to hopefully finish up chapter 4 and then get digging into orthogonal methods, QR factorization, and LU. So we left off looking at this algorithm numerically. Right? It's the up-looking Cholesky factorization. And it's based upon, if you recall, this particular Cholesky is based upon the triangular solve to compute this last column of the L matrix and then a dot product and a square root to compute L22. So that gives us this algorithm here, and then here's the implementation of it. And I think I left off, I hadn't gone into any of the details of this. So I'd like to do that today, look at the specifics of this numerical algorithm. And then I want to look at, and there is a typo there, by the way, in the book, let's see, and in the code. Yeah. So I'll fix that. And then look at other forms of Cholesky factorization that enable higher performance on machines with cache. Because the triangular solve here, unfortunately, doesn't really, it's asymptotically fast, and that was the choice that I used for methods in the book, where methods were asymptotically fast, not necessarily not necessarily exploiting cache to full benefit. So had I done that, this slide would be multiplied by a factor of about 100 in terms of length of code. It wouldn't all fit on a single slide, that's for sure. So this triangular solve then, let's see. I end up explicitly permuting the input matrix with the fill reducing ordering. That's chapter 7, so we're looking ahead a little bit. And I think I talked about this right here. This basically is pointing, CP is coming from the symbolic analysis, and I don't want to modify it. So I don't want to modify my input S, because I may want to factor another matrix with the same column pointers, the same pattern. So it doesn't change S, but it needs to copy this then into two arrays, LP, which is permanent. This isn't changed. So those are the start of each column. And then C, which is going to be a pointer which is going to be used to fill these buckets. Every column, think of as a bucket. And at the kth step, when we're computing the kth row, we're going to put, so if I'm at the kth position and I find a column J and I find an entry there, I'll put that in the jth column. And so since the rows are being computed in strictly ascending order, then when you look at every column, it's doing the transpose basically simultaneously. So at the next step, if I compute row k plus 1 and I find a non-zero there, this entry will be appended to column J. So column J is sitting here, and I know exactly how many entries are going to be. And so if I've computed so far and I say, okay, there is a row index k in column J. And then in the next row, if I find, oh, there's a k plus 1, oh, there's a k plus 10, whatever, you see it's then it will appear in strictly ascending order. So it's doing the transpose, because it's computing row by row, but storing it column by column. It's transposing it for us automatically. And that's kind of handy. So I don't have to... This algorithm, by the way, I should say, is actually not this actual code, but other code that I wrote is actually in the Cholesky factorization in Matlab. So in Matlab, what I do, and I'm just looking ahead a little bit, I do this symbolic pre-analysis. So I find all these column counts, and I find from the column counts you can get a couple things. So if you have the sum of the column counts, let's see, I don't get the row counts because I don't actually need them. So if you get the sum of the column counts, this is the total number of non-zeros in L. That's a useful number and very easy to get. Just sum them up once you have them. Remember, finding these counts, all of this work is order A time. So the symbolic analysis finds these column counts quickly, gets the total. And then it turns out that the floating point work is proportional to, actually, and the constant is 1, if I recall, the sum of the squares of the column counts is the floating point amount of floating point work that's needed in Cholesky factorization. And why that is, I would need to derive. I don't have the derivation in front of me. It's fairly straightforward. If you think of Cholesky as like Gaussian elimination, you do these outer products, it works out pretty straightforwardly to be the sum of the squares of the column counts. Well, so when I wrote the sparse Cholesky that went into Matlab, I was wanting, of course, to put in well, actually I did this before. I wrote the code and then they incorporated it in Matlab. But I wanted an algorithm that was going to be fast in practice. So I needed a method, not the one on the board here, but I needed a method that exploited dense matrix operations. So it's like what you're doing for the project right now. You try to look for common substructure and then you exploit that with the cache. But the thing of it is, what's interesting, if you look at the relative performance of, say, this algorithm, okay, this is asymptotically the same amount of work as exploiting supernodes, but it's much simpler. And if you have an extremely sparse matrix, you won't find any structure, but you'll spend time looking for it and trying to find it, and you'll actually end up slower. So these very fancy algorithms that try to get really high performance on modern machines are slower on extremely sparse matrices. But this one is better. It's faster for very, very sparse matrices. But the other one is, so this is twice as fast for very sparse matrices, very, very sparse. It's 10 times slower for matrices that, say, come out of finite element analysis. You know, you've got a three-dimensional model of an automobile trying to find its eigenvalues because you want to know, when it vibrates, will it rattle? You know, does it have modes of vibration that correspond with, say, the frequencies generated by the engine? And if it does, it'll just sort of like when you push a swing set. If you push it just at the right frequency, you throw the person off the swing if you push hard enough. And that's what causes rattle on an automobile. And that's why when you take a hammer and you bang on a car, you don't ever do that, right? But if it's an old clunker, it can change how it rattles because it's changing the frequencies. Well, an analysis like that requires a Cholesky factorization, but it's not an extremely sparse matrix. And this method here would be 10 times slower than a method which would exploit the blahs. So I tried to ask myself the question, how could I find out ahead of time? See, I don't want to say, well, pick whichever method's fastest. How do you know which is going to be fastest? You don't know. Okay. Well, what is it about cache that makes it fast? So you have a cache memory here. And you've got a large amount of memory here. And you bring data into cache, you work on it, and you put it back. And what makes cache efficient, is if the data transferred is much less than the work you're doing on that data. So I thought, well, I could take the ratio of these two terms. I could look at how much data has to flow into cache versus how much flops have to be performed. I could do this piecemeal, like, okay, this little bit of work, this little piece, this little piece. But I said, oh, well, let's just try to see if I can aggregate this information. And let's look at this ratio. Right? Let's look at the flop count divided by the number of non-zeros in L. Let's look at this number here. And I should have put the results up here. And then let's try it on some matrices. And gee, we could use some collection of matrices from real applications to do this. Do you know where we could find any? Of course, I have a set. That's the whole point of having such a set of matrices. And so what I did is I took this as, so I took my, I got 300 or 400 of sparse, symmetric, positive, definite matrices in my collection. and I ran these algorithms. I ran both of them on all these matrices. And on the x-axis then, I plotted this flop count per number of non-zeros in L. And the cool thing about this metric, which is really powerful, is that you get this directly from the symbolic analysis. It's very easy to find because you do the column counts in essentially linear time with the size of the matrix, input matrix. You get the column counts, and you can easily then sum them and sum them squared. So that's the numerator and the denominator. Okay, it's very easy to compute this ratio. And these two methods, the supernodal method and this very simple method, both need the same symbolic analysis up to a point. So they both need the column counts. So you have this flow of the code that says, okay, let's compute the symbolic analysis, let's get the tree, let's get the column counts. And no matter which method you would have picked, you don't have to know at the moment which method you're going to pick because both methods require that analysis. Okay, so this is free. Now, once you get this, the question is, can you use this to decide which method to choose? Decide which method to choose. That's kind of redundant. It's redundant and repetitive. Okay, so that's the question I had, my hypothesis. And then so I did this experimental results to see if that hypothesis was making sense. So I plotted the flop count over the non-zeros in L, and then I plotted here the relative performance. So 1 meaning equal, and 1/2 meaning, and I did it on a logarithmic scale, so it's fair on top and bottom. So this would be a 2. 2 means the supernodal method is twice as fast as this basic method you see on the screen, and 1/2 meaning the supernodal method is half as fast. And the results were stunning, really stunning. I found by experiment that there's a number of roughly about 40. And what happened is all these matrices the data kind of looked like this. There was this beautiful little S-shaped curve. I mean, there's some kind of theory behind here. Behind this deeper theory that I haven't found yet. And the peak was about 10. And it ran through roughly about 40. And I tried it on different machines. It was maybe 35. Different processors, maybe 45. But in any case, even if you choose the wrong method, the difference is the difference in performance of choosing the wrong method was a cost of at most maybe 20%. So this ratio, basically, I take this ratio, and if it's less than 40 or less, then I pick this method on the board. Otherwise, I use a supernodal method, which I'll talk about later. And experimentally, if I pick the wrong method, it's only going to cost me 20% or so in the performance. It's basically extremely accurate, astonishingly accurate predictor of performance. And 40 makes some sense, actually, because cache and the CPU is about 10 to 20. It's about that order of magnitude times faster than memory. The CPU is maybe about 10 times. If you look at the memory bus speed, for instance, and you look at bandwidth, and you look at latency, and all these different issues, performance metrics for how fast memory is, it's not very fast compared to the CPU. 10 to 20 to 40 times slower. Okay, well, so 40, that's sort of in the range of what you might expect. If this number was 3, I'd wonder, why is it 3? That seems rather strange. And if it was 1,000, I'd also wonder, there must be something wrong. But it's about 40, which makes sense, considering this relative speed of the CPU and the memory. This is about the point at which the CPU and the memory are working about the same speed. So this was a stunningly accurate metric. I had no idea it would be such an accurate predictor. I was kind of shooting in the dark, had a reasonable hypothesis, and it was amply confirmed by the experimental data. This is a kind of analysis that really is, I would say, is impossible to do with the theoretical analysis. You can't sit down with this and come up with that S-shaped curve using combinatorics and graph theory. Well, at least I can't. Maybe somebody else could. Okay. Because you'd have to think of it. You'd have to have a model of the CPU and the cache throughput, and a model of the algorithm and exactly what kind of cache misses it's going to have. I mean, it's just absurd, the complexity of trying to do that analysis. Just run the thing. And what's also very stunning about this is that the exception, you might think, oh, it's the logarithmic scale. It's a log-log scale, in fact, when I plotted this, I think. So, gee, that tends to make things line up on a line naturally. If you plot things log-log, you get straight lines oftentimes, even if the data is, But what turned out rather interesting is there are a few outliers here. Now, where my supernode method was unexpectedly slower. That's a little disappointing. But on the other hand, it's actually the exceptions that prove the rule, in a sense. Because what these matrices tell me is that there are real matrices out here that could actually cause the performance to deviate from this smooth curve. So if you asked a theoretical upper and lower bound, it'd have to incorporate this somehow. So there's a wide range of theoretical possibilities. You could fabricate matrices that would maybe go here and maybe go there. I have no idea if it could go up here or not, but there are matrices that are down here. So the theoretical curve would be wider to incorporate that, because there are in fact matrices out here. So the fact that most matrices from actual applications lie along this rather smooth curve then is all the more stronger when you know that it's possible for matrices not to lie on that curve. Actual matrices from real applications do not have to lie on the curve. Most of them do. So it's sort of like an average case complexity, experimentally speaking, right? It's about 300 or 400 matrices from extremely broad breadth, broad breadth, again, I'm repeating myself, extremely broad regions of different applications and areas that these matrices come from. So anyway, so let's look at the denominator, if you will, of this. This is this algorithm here. This is the up-looking Cholesky then, that is the algorithm that you would want to use here. And Matlab, inside backslash, then, does this symbolic analysis, looks at this, and looks at, oh, is it less than 40? And then it uses this method right here. Not exactly the same code, but I wrote both codes. I just took this one and kind of trimmed out. The one in Matlab handles complex matrices and so on and so forth. It's a little bit more full-featured than this, but not much. It's very simple, the one in Matlab. It's very comparable to this. And it's the same algorithm. This one is concise. The other one is a little bit more verbose because it has to do other things, a few other things, like I said, the complex case. Okay, so let's look at this algorithm then that's in backslash. So you're going down k by k, and there's a typo. This should say compute the L k comma colon, right? This is reversed. You can't debug a comment very easily. So you can see it right there, right? Compute it, and oh well. So at the kth step, we're going to compute the kth row of the matrix. Now, we do not yet know the non-zero pattern of the kth row. We know how many entries will be in that kth row. Well, we could have. If I would have kept the row counts, I could have computed them, but I didn't. So the very first thing we need to do is actually extract from the elimination tree the kth row subtree. So that's a very simple algorithm we looked at in Chapter 3. I've got this huge elimination tree, and I want to start with entries that correspond to non-zeros in the matrix A, and then walk up. And it's possible, see, it could look something like this. It's possible that I don't even find the leaves I mean, if I see this, that's not a problem, right? I could still start from this. Well, say I would start from this one. Suppose I would start here. And what can happen is then you just walk this path up the tree, stop at K, you know you'll hit K, and then just go to the next non-zero and walk up until you see a node that's marked. And so this will do the path decomposition explicitly. We're now finally traversing these paths. So that's what the EReach is doing, and that was back in chapter 3, if I recall. Now we need to do the triangular solve. So the first thing that has to happen is, it's actually now the C matrix, not the A matrix. The first thing that happens is this is a incremental initialization of the x vector. So the solution vector here, when I do the triangular solve, I'm only doing it for the first k minus 1 entries. But I need to compute xk, because that's going to be the diagonal. So I've got this right. I've got the first k minus 1, and I've got the kth row here. And so xk is special. And this is x1 through k minus 1, or else 0 through k minus 1 if you like, whatever. This right here is junk. There's garbage there. But I'm not going to use it, so I don't care. So this initializes xk to 0. So now there is a loop invariant here that x 0 through k is now all 0. And to make sure that happens, I have to then make sure at the bottom of this loop that x 0 through k minus 1 is now 0 at the bottom of the loop. Oh, I'm sorry. Well, 0 through k. If 0 through k, if this assertion is, by induction, if this is true, I need to then make it true at the bottom of this loop. 0 through k then is all 0. And then when I iterate to the next step, I'll set the kth entry to 0. So that satisfies the loop invariant. So I better make sure that for this to work, I better make sure at the bottom here that x 0 through k is now all 0. If this is true, I have to make sure that's true at the bottom, and then the induction works. This is writing code inductively. It's a very powerful way of thinking about code. So the first thing that happens is very straightforward. Just go through and scatter the right-hand side into, because it's sparse, right? I need to scatter it into this x vector. So this is the part in the triangular solve we do x equals b. So these entries get scattered into the x vector, and presumably the diagonal would be set too, because, and actually I could have lived dangerously. I could have supposed that C had a fully non-zero diagonal. If I make that assumption, I could have deleted this statement here, because then it'll just overwrite that anyway. Because there will be a row index k in this column of the C matrix. Any matrix that does not have such a diagonal, any matrix with a 0 on the diagonal, will not be symmetric positive definite, and Cholesky will fail, period. So, but you might have tossed in a matrix that in fact has a 0 there, or a missing entry, and you want to be able to detect it. So set the thing to 0 just as a check. So scatter the thing. Then all I do with this kth entry is then remove it. So if you will, I'm just extracting it here and then then grabbing it out of here and just writing this back to 0 again. So this is now 0 again. And now I have D is equal to the CKK entry. So it's the matrix C is what I'm factorizing. The reason I want to do that is because if you remember on the previous slide, a couple slides, I need to do this dot product here. So you need to take this this is the value d, the scalar d. And I need to subtract out L12 transpose times L12, this dot product. Now you know how to do a sparse dot product, but there's something special here in that this L12 vector is dot product with itself. What that means is every time, so, and this is this entry, this vector right here is what's going to become L12. This is L12 transpose, I suppose. So every time you see an entry there, all you have to do is subtract it, that entry squared. If this is, say, LK J, or what do I call it, I think I might call it I just need to subtract that every time I see an entry in the kth row, subtract it from D, and then take the square root when we're done. So that'll accomplish this computation. The rest of it then is the triangular solve. So that's what's happening in the algorithm for the D scalar that starts out then as CKK. Then finally there's the triangular solve. The triangular solve then, this EReach function has computed the pattern and it's put the result in the S matrix, or the S vector array. And so then we traverse over this and grab out the row index and then do that triangular solve for the ith column. So I'm not at J, I'm at I. I'm not sure why I picked I instead of J. That's kind of weird in retrospect. So it's column I. Why would I do that? I guess the reason I did that, if you think about the triangular solve is finding a row index I. Well, that does correspond to a column I. So they're one and the same here. So you can see xi right there. You're grabbing the ith entry out of the x vector. So the work that has to be done for the triangular solve, if you think of the triangular solve sweeping through every column, what it has to do with that column is the first thing it has to do is, and I have to pull up chapter 3 to look at this. Maybe that would be worth it actually, just to refresh everybody's memory. To pull up. So here's the triangular solve. I don't know if I need to make that bigger or not, but we've got to do the division by the diagonal. And then for every index larger than the diagonal, we've got to do the subtraction. So here's the code, and you're playing with this code for this current project anyway. There's the division, and then there's this gather-scatter operation that has to happen here. While in here, by the way, let's look at that. I think the EReach is further down here. Oh, I guess not. I guess it's here. Yeah, there it is. Yeah, this is the EReach code. So it doesn't try to exploit the skeleton matrix at all. It doesn't need to, because anything not in the skeleton will just be marked. I'll grab a row index and it'll be immediately marked already, so it'll be skipped. So there's really no reason to exploit, there's no need to exploit the skeleton matrix. You look at an entry and decide, oh, it's in the skeleton. Well, in constant time, I also see that it's marked, so forget it. There's no need to try to exploit that property. The skeleton matrix is only necessary if you want to find these paths without traversing them, but we're traversing them here for the EReach. We have to, so that doesn't matter. Okay, so this is that the division by the diagonal, and then at that point, then I want to zero that entry out, because basically what's happening here, the non-zero pattern of the solution is sitting right here. It's S of top, for top goes from 0 to n minus 1. Okay, so this is the non-zero pattern of the result, and I'm walking through all those entries in topological order. So as long as I set this thing to 0 now when I've extracted it, and that gives me the LKI entry. So I'm now going through the triangular solve, and I get out, I get out this entry, well, here I've drawn it already. I get out this entry I, and then if I set that back to 0 again, that'll zero out the x vector. Of course, then the question is, well, wait, you're trying to solve for x, and x is your result. Yes, but I'm also zeroing out x, and I want to put the solution. This part of the solution goes here. So the triangular solve goes down to here, right? That's what the triangular solve is doing. This entry, when transposed, this whole vector, when transposed, becomes the L12 vector. So this entry and that entry are one and the same. So I'm zeroing this out, and now I got to put this in the L matrix. So that's what's happening here. The division happens, and then that entry is then going to become. So it's now then removed. It's been computed. It's finished. It's then removed from the x vector, and it's going to be placed right here in the L matrix. Okay, so LKI then is computed. It's stored in a temporary scalar rather than leaving it in the xi vector. So here in the triangular solve you saw before, this is xi, but it's not xi anymore. It's LKI, the temporary scalar. So this then, and this is interesting here, this is the triangular solve, okay, of everything below the diagonal, and I know that the matrix is sorted because I'm creating it that way. So I know everything below the diagonal is that entry plus 1. I know the diagonal has to be present because where do I store the diagonal? Well, I'm going to put a diagonal in every entry. I know the diagonal has to be there, otherwise the matrix is not symmetric positive definite. This piece right here, then, this is not LPI plus 1, minus 1, okay? It's the C temporary. The reason there is this bucket, where have I drawn it? I guess I've erased it. If I look at the ith column, it's bigger than what I have so far. Okay, so I've only computed part of it, but I'm only doing the triangular solve with part of it, the k minus 1 submatrix of the L matrix. But that's exactly what I've computed. So the C array tells me, that C of I would point to this position right here in the L matrix. So if I look at the ith column, it's been partially filled, and the first empty spot is pointed to by C of I. That's the first empty slot. And that's the point at which I want to store the LKI entry. And so when I do the triangular solve, I want to stop right there. Right, one before CI, or C, yeah. So that's where this goes. And then there's the same triangular solve, internal nested, the most deeply nested loop. So this is where this statement right here is where the bulk of the time is spent by this algorithm. Everything else in here is proportional to either the non-zeros in L or the non-zeros in A. It's this one statement, which is order flop count, a single statement in the code. Well, I suppose the loop iterate as well. And then finally, we've computed this LKI entry, so it needs to be subtracted from D because I need to compute this dot product. Every entry in the LKI the L12 vector has to be take the sum of the squares. That's the dot product, and subtracted from D. Then this entry has to be placed because it's now finally computed. See, I've taken this right here and I've updated some of these entries in X, but they're not done yet. They're not computed yet. We can't then put these in yet. But there's one entry right here. This entry is finished now. It's the XI entry, which is LKI. And it's now got to be placed in position. And that's what this does. We find out where to put it. It goes in column I. We get the place to put it and increment the pointer for the next iteration. and then put the thing there. We know the row index, it's k. We don't have to compute it because we know we just solved for the kth row of L. And there's the value. And that's it. There's one more thing on the next slide, cleanup. For this kth iteration still, is now we've got to finish off the computation of the diagonal. Okay. At this point, if D is negative, then we don't have a symmetric positive definite matrix. That's the test for symmetric positive definiteness, that the diagonal entries have to be real and not imaginary. In other words, you can't take the square root of a negative number. So if D is 0 or negative, then we're done. Now, if you think about what happened with D started out as some number, and then a positive number was subtracted from it, right? So we started out with we must have started out with a positive number. If this CKK is 0 or negative, then there's no way that D is going to be positive. If this starts out as a positive number, it's possible for D to be negative if these decrements here, the subtractions, make it go negative. So CKK being positive is a necessary but not sufficient condition for the matrix to be symmetric positive definite. The only way to test if a matrix is symmetric positive definite, well, you can compute its eigenvalues and make sure they're all in the, I'm dyslexic, let's see, the which half plane, right? That plane. the right half, yeah, the right half plane. But it's also equivalent to check to see whether or not the diagonal here, if a Cholesky factorization exists, if and only if it's symmetric positive definite. But certainly if CKK, if any entry on the diagonal of the C matrix starts out 0 or negative, then we know right away it's not positive definite. There's no need to check. And so this gives rise to the backslash algorithm in Matlab. The first thing that it does is it asks, oh, I've got a symmetric matrix. Is it rectangular? Is it square? Oh, it's square. Let's look to see if it's symmetric. Oh, it's symmetric or not. If it's symmetric, let's look to see, let's look at its diagonal. Oh, the diagonal has a negative entry. Oh, then Cholesky will fail, so don't bother. Use LU factorization instead, or symmetric indefinite factorization, LDL transpose. But if it is symmetric and has a positive real diagonal, the diagonal can't be imaginary, then a Cholesky factorization might exist. But that's a necessary, not sufficient condition. So you might try it and realize, oops, I made a mistake, and then you punt. You throw away all the work you did entirely, even the symbolic analysis, everything, and do an LU factorization instead. Backslash is rather costly because it doesn't necessarily even know that you're, like if you're trying to do a triangular solve, think of calling CSL solve. You know the matrix is lower triangular, right? Well, you think you know. Backslash doesn't know that. It has to look at the matrix and say, oh, look, it's lower triangular. Let me use a lower triangular solver. So anyway, this is the test here. If D is negative, then we return a failure. Otherwise, then we've computed the kth step, and we need to now compute the diagonal entry right here. This is LKK. And that's what's done here. See, this is now the first time that the CK entry has been incremented. I'm going to take the square root, and we're done. And then finally, the very last step, and this is a very easy thing to forget, is you've got to terminate the last column. The LP vector, the reason I have to do this here, this is the only place, this is the second place where I've touched LP. It's here. I haven't touched LP before. I use it, but I haven't modified it. The reason is at the very beginning here, I copy it over from the symbolic analysis. But the symbolic analysis only keeps track of the first 0 through n-1 entries. It doesn't actually store, I think it doesn't actually store the last one. Either that or it might, but it doesn't. I don't store this. I forget exactly which one I do. But this only creates the first n, not the last terminal value. So I have to do that at the very end. I could have done it here, because this, whoops, where was I? Here. I mean, this statement right here doesn't depend on any of the previous computations. CP is a constant. I could have put this statement at the very top, right here. Yeah, so CP of n is defined, but C is an array of size n. And I just don't copy it all there. I don't know. I could have, I guess in retrospect, I could have removed a one line of code, that last line of code. Had I made C a vector of size n plus 1, then I could just do this less than equal to n, and that would delete one line of code. I didn't do that. Whatever. So that is the, and actually, you know, deleting that one line of code would have been handy as I look at it in retrospect. Because if you look at the way the book is formatted, it could have, I could have fit the whole code on one page. Now, as it is, one line of code breaks the page, so details. Anyway, so that's the numerical Cholesky factorization. What I do then is I store the result here, and whoops, there's EReach. Okay, yeah, that's it. Oh, there's EReach again. I recopied it here just so it would be available for me rather than having to go look for it. Well, I looked for it. Anyway, so I explained this to you already. So that's the up-looking Cholesky. That is the triangular solve and the dot product. But it's not the only way to do it. Okay, and that's what I'm going to talk about next, is there are other ways of doing it. This is a very simple way of doing it. Very clean, very elegant, very short code. This is not quite as simple. If written without exploiting dense matrix kernels or supernodes and whatnot, the left-looking method is just about as simple as the up-looking method in terms of the code difficulty. But the left-looking method allows us to make better use of supernodes. So that's what I want to talk about next. You won't find code for this in the book, though, because this code's the left-looking supernodal code is around 10,000 lines of code instead of 50. But here's the idea. I want to at least explain the idea so you can have at least some of the theory behind the faster methods. These are not asymptotically faster, remember, though. These are just faster in practice because they take better use of cache. Make better use of cache. So this is a working Matlab prototype. It doesn't try to exploit Sparse at all. It just creates a zero dense matrix. But it's based upon this 3x3 block matrix multiply. Okay, so you can take the A matrix and slice it and dice it so that A11 is the first k minus 1 rows and columns of the matrix. And this is a single column, and that's a single column. And then this piece right here would be of size n minus k. So this is k by minus 1 by k minus 1. This is a scalar. A22 is a scalar. And this is n minus k by n minus k. If I do that, then I can also slice and dice the L matrix in the same way. So this looks familiar. This right here is the k minus 1 by k minus 1 L11 matrix. But the thing below it is then sliced a little differently. Well, actually, in the way I did the 2x2 block factorization is I said this is n minus 1 by n minus 1. And then this is just the last one. So this is the kth row again. This is the kth column. But I've now written the block matrix multiply so that it exposes that kth row and kth column explicitly. Okay. Now, now what you can do is you can write down 3 different equations. And namely, it's these 3 pieces right here. Okay, the A12 part, the A22 part, and the A32 part. Actually, it only turns out you need these 2. But let's look at all 3 of these. Now, let's suppose by induction that I have computed the first k-1 columns of L. In other words, let's suppose by induction that I have L11, L12 transpose, and L31. So I'm computing L column by column. And then the question that we ask then, if I have the first k-1 columns of L, can I compute the kth column of L? And if I can, then I finish my inductive proof. And also you have to then also worry about the base case, which is pretty straightforward. So to do this, we need to actually write down 2 equations. If I write down the A12 equation, all I get is this one here that we had for the triangular solve. We get that L11, L12 equals A12. But by induction, I know L11 and I know L12 already. That's L12 transpose. So that equation doesn't help us any. It doesn't tell us anything new. So it's not needed. But the next equation is very interesting. The next equation says that L12 transpose L12 plus L22 squared equals A22. This is useful because now we're talking about values that we know by induction, but this one we don't know. We want to compute it. So that gives us a way of computing L22. We can do the dot product and the square root. That gives us L22. Then this next equation comes from the following. If I take the matrix multiply for this, again, with block matrix multiply, you just pretend that you're dealing with scalars. You just have to make sure that A times B is not the same thing as B times A, and then you're set. You say multiply this times this third column by this second, I'm sorry, the third column. Did you notice that? You know, the third row times the second column. Okay. And we get this, we get L31 times A12 plus L32 times A22 plus L33 times 0 equals, right, because that's not there, equals A32. Well, if we know L22, I've missed something. L31, what did I miss? I should get this equation down here, and I'm not. L32 times L. Oh, this is L here. Okay. So now what I can do is I don't need this. This is 0. I know L31. I know A12. I now know L22. I can solve for L32. Right? This equation here, I can algebraically solve for the L32 vector, column vector, and that gives me this equation. This equation, and I've got 10 seconds left, is a matrix vector multiplication. L31 is a matrix. L12 is a vector, subtracted from a vector, and then scaled. So this is a matrix vector operation. This is a vector-vector. This is a matrix vector operation. So what I've done is I've recast Cholesky factorization as a collection of dot products and matrix vector multiplies. And we know how to do matrix vector multiplies. So we'll look at that, and then on Wednesday, how we implement this, how we might implement this algorithm. But there's the Matlab code. You can look ahead and see how that works. So I'll see you Wednesday. Thank you.